So for chapter 21, we want to talk a little bit more about hypothesis testing. And remember, the p-value is not the probability the null hypothesis is true. Might be easier if you think about this in terms of if, the null hypothesis is true, what was the probability of us observing the statistic that we did? Or back in conditional probability, our p-value is the probability of the observed statistic value given the null is true. So if this is very low, and there's two parts to think about this, our observed statistic value, well, we have that. We know the probability of having that. That's 100%. The only thing that can change this probability is the probability of the null hypothesis being true. We have the statistic. That happened. That's 100%. So it's only the null that's changing this probability. So as we said, we want small p-values. Really small p-values increase my confidence that my null hypothesis is not correct. It provides that evidence. But the question is, how small of a p-value do I need? And we haven't really gotten too much into that. Like these smaller and smaller p-values. We've been talking about we want these small p-values because it'll help me out. That the smaller it is, the better the evidence. So we call that the significance level. When we decide how small p needs to be, we're choosing our significance level. And that's also called the alpha value. So this is the threshold that we set, that if our p-value is lower than that, we reject the null hypothesis. And then we can call those results statistically significant. So remember, the alpha value is not dependent upon my statistic. It's not dependent upon the test. It is a value that we set before we even run a test. Now, when we choose this level, in some cases you get to choose it. Some cases it'll be told to you what you need to use for your alpha level. When choosing it, we're really saying, how much evidence do I need to reject the null? And this can be a tough question. But the way we work at this is there are two main things we have to consider when we choose this. The first one is, how plausible is the null hypothesis? If the null hypothesis represents an assumption that people have believed in for a long time, you're going to need strong evidence, which is a small alpha value, to persuade them. To eliminate established ideas often requires a strong amount of evidence or a small alpha. The other thing is, what are the consequences of rejecting the null? If rejecting the null in favor of the alternative means making expensive changes, you need strong evidence. If the consequences are possibly life-threatening, you need very strong evidence. So this is going to help us decide on these alpha levels. So the first thing is, very common alpha level is 0.01. And it's common just because statisticians have used it. It means we have a 1% chance of observing our statistic assuming the null is true. And this has been used for things like, how safe are airbags? How good is this medication? Should we buy a new bomb detection kit? And we talk about that as an example question in class. That bomb detection needs to be pretty accurate. People's lives depend on this kind of information. We demand strong evidence or small alphas. The next very common one is 0.05. And if you read the textbook, they have a story about where this one seems to have come from. And it's just a number someone came up with. It wasn't a hard and fast rule. There's no mathematical proof. This was just a person's idea that he felt a 1 in 20 chance of being just randomly come up. That would be good enough in a lot of cases. So it's an interesting story behind it. Okay? We use this for, if we don't know what else to use, we'll use this a lot of times. If we're just not quite sure, we can use this one. Of course, next one we have, this one doesn't come up a whole lot, is alpha is 0.1, or alpha level's 10 sometimes you'll hear people say. This means we have less than a 10% chance of observing the statistic if the null hypothesis was true. And this would be questions like, do people prefer pepperoni pizza over, say, hamburger? This is for things that could be important, but no one's life is depending on the answer. Now I'm kind of hungry for some pizza. But remember, different people are going to use different significance levels. So if someone's a doctor, they're going to demand that alpha level of 0.01, a 1% chance of the result if the null was true. Someone else, this researcher still in a lab, no one's life is depending on their work right then, they might use an alpha of 0.05. And of course, carrying boxes can make people hungry. This person might use their alpha of 0.1. Now, statistical significance, we want to remember, is not the same as practical significance. And this is what today's lesson started off as. There's a lot of vocabulary and kind of understanding what's happening. So if I can reject the null at a reasonable level, 0.01 or 0.05, I don't have to make a lot of allowances. I can pretty much say, yeah, then we believe there's evidence that effect or difference is actually there. So the probability of me finding that result just by chance was below 1% or below 5%. That's pretty good evidence something's actually going on. But the effect itself might not be very big. So let's suppose you had an uncle that taught statistics. Your dad and your uncle, they're related, they talk a lot, and you decide you want to go to a couple different colleges. Your dad, though, has said, I want you to go to your second choice school because it turns out your top choice is more expensive. And they found a statistically significant difference between the annual tuition of both. And they found a p-value of 0.04. So they have a statistically significant result. But is it practically significant? Does it matter? In this case, well, what if they found that the difference was $180 a year? The results are statistically significant, but are they practically significant? If you're talking about a tuition, annual tuition, which in some places $14,000, $15,000, $20,000 potentially, $100 difference in tuition might not, or $200 difference, just might not be that practical. Is it enough to change and outweigh all the other choices that went into your top choice and your second choice? That's that discussion people have to have about. Statistical significance is also going to be a judgment call. But sometimes in some situations we can say, well, a practical significance would be a difference of $100. We might be able to be given that kind of information. So, because on the other hand, let's say we have a drug and it's going to help people who are getting cured, and we show a 10% improvement. That might be of practical significance. But proving statistical significance at that level in a study with like less than 200 people, that could be very hard to find. It can be very hard to find that statistical significance when we have our small sample sizes. So you have to set the alpha levels before you run the test. This way you can also make sure if my alpha is 0.05, I know I need to have enough people in my trials. It also helps keep us honest. Because sometimes, let's say we get a little tiny bit of a difference. It's 0.0499. That meets it for 0.05. But let's say it was 0.051. Just barely didn't meet the statistically significant event. Well, let's say what I'm evaluating is something I'm really invested in. I really want to make sure people are getting healthy, and I do my study, and I find out, and I finish, and it's 0.051. I barely didn't make it. What this should do is, if completely honest and ethical broker, I should be going out, and as a researcher, going out and looking for a bigger sample size. I should keep gathering data. But it is kind of nice. Your uncle teaches statistics, so you can end up being a couple standard deviations above the mean. But let's talk about this. We've got our alpha values. Now remember, in our two-tailed test, if we look over here, okay, so recall, when we're dealing with a two-tailed test, we're going to split our alpha. We're going to have to find one side and then double it to get our area. So if my alpha is set for 0.01, then I need to use 99% confidence intervals. It's no longer up to me what I'm going to use. Once I have an alpha, my confidence level is going to be given to me. Now, if I have a 99% confidence, I have my alpha is split between both tails, then that must mean each tail contains 0.005. And we know we put 0.005 in our calculator, find our critical values, it's 2.58. Inverse norm, and we'll find our critical value of 2.58. If I had a 5% alpha level 0.05, well, my confidence interval, I'm going to use 95%. I'm making it up so that this makes it to 100 in the two-tail test. Of course, if I have 5% in my alpha, I cut that in half. I have 2.5% in each tail. My critical value for 0.025, 1.96. Last option I have a 10% alpha level, the last of the most common ones. This is going to be a 90% confidence interval is what I'm going to have to construct. The 10% alpha, I need a 90% confidence. That leaves me 5% in each tail and a critical value of 1.645. So this is that two-tail test when I was going to find the area in one and then double it. Right? So let's go ahead. What if we just had that one-tailed test? Okay. Well, if I'm doing a confidence interval for a one-sided test, remember, if we look up here, my confidence intervals are naturally two-sided. Okay, we're going our p hat plus and minus my margin of error. It's natural that they have a two-sided test. When we go to a one-sided test, there's going to be some slight differences. First, my alpha is at 0.01. Now my confidence level needs to be 98%. I actually take that 1%, double it, and remove it from the 100. The amount of alpha in each tail, all of it. I only have a one-tailed test. As you can see, it's pointed out, that's my alpha. All alpha. That means my critical value is going to be 2.33. So if I had a 5% alpha, I double it, remove it from 100, my confidence level is 90% then. The amount of alpha in each tail, well, again, I have 5%, I have one tail, it needs to be 0.05 and a critical value of 1.645. So our last chance here, if I have an alpha of 10, of 0.1, it's often said 10%. Alpha of 0.1, I double it, that's 0.2, remove it from 1, that gives me an 80% confidence interval. That was that last confidence interval. We said these are the most common confidence intervals at 98%. That's where it's coming from. 90% where it's coming from, and 80%. That's where that 80% came from since we didn't see it on the last slide. Now again, amount of alpha in each tail, I only have one alpha, I have one tail, it needs to be all of it. And critical value is going to give me is 1.28. So if I get more than 1.28 standard deviations away from the mean with my test statistic, I'm going to have statistical significance. I finally got far enough away. And that's it. That's all we covered today. So go back over. Let's pray around, practice your alphas, read the rest of the chapter. And go over these. It's really about being able to solve this table, not about knowing it. Big thing to remember, if you have a two-sided or two-tail test, a two-sided test, your alpha levels and your confidence intervals work with each other very nicely. And don't forget, you have two tails, so you cut your alpha in half. It's your one-sided, you have to remember to double the alpha before you find your confidence interval. Look forward to seeing everyone in class.